All right, so with Limacons, we just graphed these on our calculator and we noticed some things. So if the constant would be like these twos, like the things being added or subtracted to the number times cosine or number times sine. If that's bigger than the coefficient, then there is no inner loop. All right, so examples of that would be like not this, but like if we made this 1, there's no loop. If we made this like 5 and this 4, there's like a dimple, but there's no loop. All right. And the next blank here is the blank becomes more defined the closer the value of the coefficient gets to the constant. All right, that would be the dimple, which has to be a mathematical term because it's in the notes. So what does that mean? Well, as you make this coefficient closer to 5, that dimple is going to become more defined. And it looks more like a heart, which is why it's called cardioid, obviously, because cardio means heart. And then once the constant becomes less than the coefficient, so that's the constant, this is the coefficient, then you get that loop. Now, does anyone notice a connection between B and A and like the length of the loop? So when B is 6, when B is 5 and A is 6, the loop has a length of 1. And then if I make this like, let's make this an 8, now the loop is 3. Now if I change this to like a 2 and make this a 5, the Limacon changed its size, but the loop is still 3 units. Does anyone see a connection between like the length of the loop and like these numbers? Play around with it for a second. Like, all right, let's make this 1. Do you think the loop is going to get bigger or smaller? Bigger? Nice. That's going to be 4. So you could find the length of the loop. Anyone see a connection? No. I like subtracting these numbers. So like the difference between B and A will tell you the length of the loop. So that's why it's 4, because 5 minus 1 is 4. If I made this like a 3, now 5 minus 3 is 2. So the loop is going to be 2 units long. All right, and these little rules help you when you're graphing because, you know, plotting polar points isn't the easiest thing. So it's good to have like other rules to refer to when you're graphing this. So the inner loop. Yes. The inner loop will have a length of A minus B. And then the outer loop, so like the actual Limacon, like the bigger circle, let's see if we see connection between A and B and the length of the loop. So like right now, this big loop has a length of 8. 1, 2, 3, 4, 5, 6, 7, 8, 3 and 5. Let's say I make this 2 and 3. Now the bigger loop has a length of 5. Does anyone see connection between these two numbers and the length of the big loop? Make that 1, we'll make this 5. Yes. Yeah, it's just a sum. So the sum of these numbers will give you the length of the bigger loop. And we'll see why that happens, but if you know these rules at the beginning, then it helps when you graph. All right, so A plus B. All right, and then other things to look for is just like the orientation of these Limacons. So when A is bigger than B, all right, so A is the coefficient and B is the constant. So that would be this case here. There will be an inner loop. So in all these pictures, we want to put a loop. In all these pictures here, we want to put a no loop. So remember, just like yesterday when we did cardioids, sine is going to be symmetric over the y-axis, and cosine is going to be symmetric over the x-axis. That's because sine of theta is equal to y over r, and cosine of theta is equal to x over r. All right, so that's how I think of it. So if sine is positive, so if the sine is positive with like a lemacon with sine in it, so that's confusing because those two words are spelled differently but sound the same. What's that, like a homophone or a homograph? I forget, something in English. But positive means it's going to go in the positive direction, the big part. So like the big loop will be in the positive direction, and that's up for sine because it's already symmetric over the y-axis. And then if the sine is negative, then it's going to be facing down. So the big part of the loop will be facing down. Where do you start drawing these? Like, there's really no good place to start. You tell a lot about a person about where they start drawing their lemacon. All right, and so cosine is symmetric over the x-axis. So if that had a loop, it would kind of look like this. And they're actually way easier to draw, like on the polar axes, not like drawing a freehand is kind of hard, in my opinion. So cosine, if there's a negative, is going to be facing in the negative direction. Right, again, we'll learn how to graph these by like, that was a bad one. We'll learn how to graph these by using like the rectangular graph. But again, knowing these things will help. All right, and it's the same idea for when A is less than B, except it's going to have a dimple instead of a loop. So it's going to look more like a heart. So the big part of the heart, or the cardioid, will be facing in the positive direction, which is up in this case because it's sine, and positive is up on the y-axis. And on the y-axis, negative would be down, so the big part would be facing down. All right, and then cosine would look like this. And cosine, when the sign is negative, would look like this. Cool. All right, so knowing these little rules here just kind of help you graph, because you can check your work, and if you get stuck, you can fall back on these. But you don't have to memorize these rules and draw it. We're gonna now, I'll show you how to do it similar to how we did rose curves and cardioids. So like that, we first graph the rectangular function. Why is this? I guess that'll work. And this gotta be full screen. All right, should have done that before. All right, so first graph the rectangular function. So we're gonna graph sort of like an X and Y axis, but we'll call it the R axis and the theta axis. All right, and we just need one period. So that's 2 pi. So and a half a period would be pi, and a half of that would be pi over 2. So that's 1/4 of a period, which is an increment. So pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. So this would have a midline at 2 and an amplitude of 4. So it'd go up 6, 2 plus 4 is 6, 2 minus 4 is -2. All right, so this is cosine with a positive amplitude. So it's going to start at the top and then hit the middle, and then the minimum, and then the middle, and then the max. And then connect the dots. All right, so sketch the tangent lines first. Where on the rectangular graph is the inner loop? All right, so first, the tangent lines are sort of like when we first started graphing these rose curves, when we had those petals. Anytime the R was equal to 0, we put like a dotted line through that angle. So because we knew that on our polar graph, like the curve would be getting closer to that tangent line, like as we rotated the angle, because when R is 0, we're going to be right at the origin or right at the pole. So the same thing is true for Limacons. So anywhere where it crosses the like theta axis, or like anywhere where r is going to be 0, we want to find those points so that we could then sketch tangent lines on our polar axis, and it makes graphing a lot easier. And I'll explain why it makes it easier when we graph. So that's going to be right here and right here. All right, so that's where r is equal to 0. So to find that, we need to throw it back to when we did trig equations. So we plug 0 in for r and then solve this here. But luckily, these trig equations are never going to be too complicated. Since we're only dealing with sine and cosine, we're basically looking for, like, there are always going to be angles that have like 30 or 60 degree reference angles, because it's usually going to equal 0 when like cosine of theta would be like -1/2, because -1/2 times 4 is -2. That plus 2 is 0. So just solve this like normally, like subtract 2 on both sides and then divide by 4. So it's -2/4, which is -1/2. All right, so we know that the cosine, so that's -1/2. We know that the cosine of 60 degrees is equal to +1/2. But since we need -1/2, they have to be in negative cosine quadrants. So like A, S, T, C. So it's going to be in quadrants 2 and 3. That's where cosine is negative. So the two solutions would be a 60 degree reference angle in quadrant 2, which is 120, or as a radian angle, that would be 2 pi over 3. And then a 60 degree reference angle in quadrant 3 would be 4 pi over 3. So those are our two x-intercepts, 2 pi over 3 and 4 pi over 3. And we want to draw tangent lines through those angles, like dotted lines on the polar graph. So 2 pi over 3 looks like that. 4 pi over 3 would be there. All right, so that's going to help guide us when we are making our loops. And that's why it's easier to like sketch it like this than freehand. All right, so since our biggest R point is 6, we can make each of these radiuses be 1 unit long. So like 1, 2, 3, 4, 5, 6. All right, so we're going to start when theta equals 0, R is 6. So that means, all right, we're facing this way because that's where theta is 0 and R is 6. So that's our first point. And then from theta equals 0 to pi over 2, R decreases. So as we rotate from 0 to pi over 2, we're going to be getting closer to the pole, like the origin. And at pi over 2, R is going to be 2. So we can plot that point first. All right, and so you imagine like you're facing this way and you're holding like a stick out that's 6 units long, and then you rotate 90 degrees. And as you rotate, your stick shrinks in length to 2 units long. So it's like, it starts out here, and then we're getting, as we rotate to 90, we're getting closer to the pole. So notice how we go from 0 to 90, R is decreasing from 6 to 2. All right. Now from pi over 2 to 2 pi over 3, so like on this little interval here, it's going to shrink from 2 to 0. So that's why we have the tangent line. Like as we get closer to it, it's going to, like, tangent means it's going to get infinitely closer to that line and never touch it. So that's how that dotted line helps us. We know we don't want to cross it without hitting the origin. All right. And now from 2 pi over 3 to pi, so from here to here, so 2 pi over 3 to pi, R goes from 0 to -2. So from this way, it's 0. That's why it's right in the pole. Here, it's -2. So that would have to go, like, as you rotate from here to here, it would it would go out to 2 again. Because -2 means you go like in the opposite direction. All right, so now like we're facing here, like towards pi, if we're at this point, but we went in reverse because r was -2. And then from pi to 4 pi over 3, all right, so from pi to 4 pi over 3, r is now increasing from -2 to 0. So -2 would be like behind this angle, and then it gets closer to the pole, like that. And that creates our loop. So our loop is always gonna occur when r is negative. So like this part of the graph is where our loop is happening, anywhere below the x-axis or the r-axis. But if it's never below the r-axis, if r is never negative, then you don't have the loop. And that's why some of these have loops and some of them don't when we originally graphed these on our calculator. All right, so now we're at pi is -2. All right, and then we did 4 pi over 3. So now we're at 4 pi over 3, so we're facing this way. And from 4 pi over 3 to 3 pi over 2, it's going to increase to 2. So like 1, 2. So it's going to be getting longer. It's like right there. And then from 3 pi over 2 to 2 pi, so from here to here, it's going to, r is going to keep increasing. So it's going to keep getting farther and farther away from the pole until we hit 6. And there's our Limacon. No one else sees Squidward? Am I just going crazy? What? You don't see Squidward?
Maybe I'd seen it.
All right, so take this, rotate it, zoom in. All right, it's not zooming. So I have to just redraw it bigger. All right, if you're watching this on video, you can fast forward. I mean, Squidward's nose is like up. It's not like hanging down.
Yeah, so I think it kind of looks like Spider-Man.
With the, I could see like with the web of like the polar graph, oh, his eyes usually like together. And he's got like the mouth that like goes like this.
I'm sorry, what?
I mean, Squidward's nose usually hangs down, but like if his, all right, you know what? I thought you were with me. Okay, so there's our first Limacon. Congratulations. You always remember this moment. First time you graphed one. All right, so sketch the tangent line first. One in the rectangular graph is the inner loop. It's this part that I highlighted. Identify the values of theta for which one full curve is traced out. All right, that's just going to be from 0 to 2 pi because that's one full period. So if we kept going, it would just keep repeating all the same values. All right, let's try another one. So we got r equals 6 minus 12 cosine theta. So that will have a midline of 6 and an amplitude of 12. So 6 plus 12 is 18. 6 minus 12 is -6. And we'll do a full period, so 2 pi. And so half period is pi. Half of that is pi over 2. Then that's an increment because that's 1/4 of 2 pi. So pi over 2, 2 pi over 2, 3 pi over 2. And now we'll graph it. So it's cosine, so it's got to start at the max or the min, but the amplitude is negative. So it's going to start at the bottom, like Drake. And then it goes up to the midline, and then to the max, then back to the midline, then back to the min. All right, so learning from what we did last time, we're going to expect the inner loop to occur where r is negative. So like on this part and on this part. So when we first start graphing, it's going to be like half of our inner loop. And then when we finish graphing, it's going to finish our inner loop. And we want to identify the tangent lines which occur at these x-intercepts. So like right here and right here. All right, and that's theta, but also where r equals 0. Sort of like how the x-axis is where y equals 0. So we could take r, plug in 0 for r, and then solve for theta. So subtract 6, divide by negative 12, and you get positive 1/2 is equal to the cosine of theta. So subtract 6, divide by negative 12, negative 6 over negative 12 is 1/2. All right, so then theta is going to be pi over 3 and 5 pi over 3. So that's something you need to remember and review. Cosine of 60 is 1/2, and cosine is positive in quadrants 1 and 4. So 60 and 300 are the two angles between 0 and 360 that you can take the cosine of and get 1/2. And in radians, 60 is pi over 3, and 300 is 5 pi over 3. So I'm going to draw a dotted line through pi over 3. And then another line here through 5 pi over 3. And that'll help guide our loops. All right, and then I'll also indicate that on my graph here. So I could use those points. All right, now we have enough points to sketch this out. So from 0, when theta is 0, r is negative 6. So even though we're facing in this direction, since r is negative 6, we got to move back 6. Now let's see, we got 1, 2, 3, 4, 5, 6, 7, 8. So let's make, we'll make each tick mark worth 3. So this will be 3, 6, 9, 12, 15, 18. So that we could fit everything. So then 6 would just be like 2 units out right there. So we're going to start right here at 0, negative 6, because 0 is facing this direction, but negative 6 means we move in reverse. All right, and then from 0 to pi over 3, r is increasing from negative 6 to 0. So it's going to be getting closer to the pole that way. So that's like 1/2 of our inner loop. So we started off here, and then we rotate from 0 to pi over 3, but we're kind of working in reverse because r is going from 6 to 0. And then from pi over 3 to pi over 2, so from here to here, r is increasing from 0 to 6. All right, right there. And then from pi over 2 to pi, so from here to here, it's increasing from 6 to 18. So 6, 9, 12, 15, 18. So from here to here, it's kind of like spiraling out. Oh, someone told me yesterday. I think it was, who was it? Someone here? Yeah, snails. That's why it looks like, kind of looks like a snail in a way. Like now, it kind of ends up not being a snail, but like in the middle of it looks like a snail. There you go, great call. SnailCon. We should start our own festival, like SnailCon, like Comic-Con. And we'll bring Gary from SpongeBob, because he's a snail. All right, so now we'll keep going. So that's at pi is 18. And then from pi to 3 pi over 2, it's going to shrink from 18 to 6. So here's 6. So 18 to 6. So it's coming in. As we rotate, it's coming closer to the pole. And then from 3 pi over 2 to 5 pi over 3, so like on this little interval here, it's going from 6 to 0. So it's going to like right along that tangent line right there. And then from 3 pi over 2 from 5 pi over 3 to 2 pi, the radius goes from 0 to -6. So as we rotate here, it's going from 0 to -6. So it's going to be going in reverse. R is going from 0 to -6. So it's moving away in that direction. And then we finish our inner loop. You guys want to know something terrible? I'm going to ruin your childhood. Fruit Loops, they're all the same flavor.
No.
Yeah, all the different colors, doesn't matter. It's just they all taste the same. I know.
That's shitty.
I figured you gotta learn that now before you go any farther in
I'm
life.
telling you, the green ones, they're not like the others.
All right.
It's fine.
H. So now this one, we got B is bigger than A. So how is this going to be different from the other two? Did I skip a page? No. Why is it starting at F? Whatever. What can we expect that's going to be weird about this one? Because now the coefficient is less than the constant. Yes. Dimple. Very good. Very good. So we're not going to have an inner loop. Very good. So let's sketch this one. And remember, the inner loop occurs when the points are below the x-axis or the r-axis. So if you look at this graph, it's never going to be below the x-axis because it has like a vertical shift of 6 and an amplitude of 2. So it's never going to dip below the x-axis or the r-axis. This is theta, or the theta axis here. It's never going to be r equals 0. All right, and this is r. And so it's sine. So here's 2 pi. Here's pi. Here's pi over 2. Here's 3 pi over 2. So we're going to start in the middle. And then we're going to go up. And then, like Marin Morris, we'll meet him in the middle. And then go down and back up. All right, so that one looks like it makes sense. Boom, boom, boom. Okay, so this one's going to be like a weird circle-y sort of thing. It's going to not have a loop, but it's going to be symmetric over the y-axis because it's sine, but it's not going to have a loop. So we start here at 0, 6. So let's mark off these first. Let's make sure. Yeah, we got enough room. There's 8 of these. So 1, 2, 3, 4, 5, 6, 7, 8. So 6 would be right here. And then pi over 2, it's going to increase to 8. And then pi, it's going to decrease back down to 6. And then 3 pi over 2, r is going to decrease to 4. 1, 2, 3, 4. And then it's going to increase back there. So if you want to add a few more points to like just make this a little nicer, you can look at where the sine of theta is going to equal 1/2. So that would occur at like when theta is equal to pi over 6, then r is going to be 7. Because I know the sine of pi over 6 or 30 is 1/2. A half of 2 is 1. 1 plus 6 is 7. So you can add another point there. And then since it's symmetric over the y-axis, it'll also have a point right there. There you go. What am I doing? 6. That should be 7. So it'd be right there. Never mind. So now you could you have, a few extra points to round this about. And then also, this will be -1/2 when theta is a 30-degree reference angle in quadrant 3. So that would be 7 pi over 6. R would be 5 because it's 6 plus 2 times -1/2. So 5 would be like here. 1, 2, 3, 4, 5. And then it's symmetric over the y-axis. So 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. There you go. And then you can just connect the dots. You don't need those 4 extra points, but they help. And now you graph that. That's pretty cool. And you're right, it does look like Spider-Man, or like a spider web. All right. I'll do these last 2 together, just to get the hang of it. If you get the hang of it and you want to start the homework, you can, but I'll do these last 2. All right, so we got, remember, there's nothing due next class. Next class, you have time to finish up the homework, and then it's all due, class after that. All right, so we got r equals 8 minus 16 sine theta. So that would have a midline at 8. So like right here. And then it goes up 16. So 8 plus 16 is 24. That's the maximum. And the minimum would be 16 below 8. So like negative 8. And a full period is 2 pi. Half of that is pi. Half of that is pi over 2. So that's your increment, 1/4 of the period. So pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2, which is 2 pi. All right, so this will start at the middle because it's sine. But then each increment after the first point is going to go down because it's reflected. It's got a negative amplitude. And then it goes back up, back to the top, and then back to here. All right, so this is great learning new stuff and also reviewing the old stuff. All right, now we can connect the dots. And from past experience, we can expect that the loop will occur right on this interval here, because that's where the r is negative, and that's how we get our loop. We start going in reverse, like Missy Elliott. So now we want to find these 2 points so we can make our tangent lines. So that's always going to occur when r equals 0. So we take this and replace r with 0, and then solve for theta. So subtract 8, divide by 16, so you get 1/2. So that means r will be 0 when theta is pi over 6, which is right here, or 5 pi over 6. So on our graph, we'll sketch those tangent lines. Pi over 6. Bang. All right, so now we want to fix our scale on our graph because we only got 8 spots and the maximum r is 24. So I would make each radius equal to 3. So 3, 6, 9, 12, 15, 18, 21, 24. So each r is equal to 3 and we can fit everything. All right, so we start off at theta equals 0 and r is 8. So 3, 6, 9. So it's going to be like a little before 9. It's going to be like right here. All right, now from 0 to pi over 6, r is going to decrease from 8 to 0. So it's kind of like tough because there's not a lot of room, but you got to like get closer to the tangent line. So as you rotate from 0 to pi over 6, you're coming in towards the pole. And then from pi over 6 to 90, we see that r is becoming more negative. So from here over here, r is going from 0 to negative 8. So we got to graph it in reverse. And then, so pi over 2 comma negative 8 would be right here, because pi over 2 is this way, but negative 8, you go in reverse 8. So from here to here, it's going to be, r is going to be getting farther away from the pole because we're going from r equals 0 to negative 8. All right, then from pi over 2 to 5 pi over 6, so from like here to here, r is going from negative 8 to 0. So it's going to be getting closer to the pole again. And at this point, you might be a little confused. You're like, what is this? Are these like 2 loops? What's going on here? But then if you think back to like everything we talked about at the beginning of class, All right, this is a sign where the sign is negative, so it's not cosine, and that's not a plus sign. So it's going to be looking like this. So like in our picture here, like this part's the inner loop. This is just part of our bigger loop, but this is our inner loop because it's sine, so it should be symmetric over the y-axis. All right, so now we're at, we just went to pi. Oh wait, so now we just rotated from pi over 2 to 5 pi over 6. And now from 5 pi over 6 to pi, r is going to get bigger from 0 to 8. So 3, 6, 9, that'll be right there. And then from pi to 3 pi over 2, r is going to grow from 8 to 24. So as we rotate from pi to 3 pi over 2, r is getting bigger. So we're getting farther away from the pole. And then from 3 pi over 2 to 2 pi, it's going to decrease from 24 to 8. So as we rotate, it's going to get closer and closer to the pole. And there we go. There's another Limacon. Cool. Got time for one more? All right, sweet. All right, so last one, and then you have all these, and then tomorrow, please ask for help if you need any help with the homework, and we could go over anything you want. And I'll share the answer keys. We'll review 2 days next week, and then we'll take our test. So J, we're going to do our rectangular graph. So that has a midline of 8 and a maximum of 24 because the amplitude is 16. So 8 plus 16 is 24. 8 minus 16 is negative 8. It's sine, so it goes like middle, max, middle, min, middle. So that's 2 pi, that's pi over 2, that's 3 pi over 2. All right, connect the dots. All right, we expect our loop to occur here where it's below the x-axis. All right, if you just, I'll do this part quickly, and if you need help with it, just let me know. But if you set that equal to 0, you get theta is equal to 7 pi over 6 or 11 pi over 6. Because if you subtract 8 and divide by 16, you would get sine theta is equal to negative 1/2. All right, and those are the two angles that work. So I'm going to draw my tangent lines. All right, so we start at 8. I'm going to use the same scale because our maximum is 24. So 8's going to be like 2 and a little bit this way. And then from 0 to pi over 2, it's going to grow from 8 to 24. So as we rotate from 0 to pi over 2, we're going to get farther away from the pole. And then from pi over 2 to pi, the r goes from 24 to 8. So it's going to get closer. So 1, 2, 3 right here. So it's going to get closer to the x-axis, or really the polar axis. All right, and then it's going, here is 7 pi over 6. So as we rotate from pi to 7 pi over 6, r goes from 8 to 0. So that's why we got to get closer to the tangent line. And then from 7 pi over 6, which is here, since r is negative, we're going to go this way, to 3 pi over 2, which is here. We have the point negative 8 comma 3 pi over 2, which would have to be away from here because r is negative. So we rotate that way, and we're there. And then from 3 pi over 2 to 11 pi over 6, we're coming back to the pole. So we get closer to that tangent line. And now from 11 pi over 6 to 2 pi, it's going from 0 to 8. So we're going outward like that. And there it is. So let me end this recording.